And at this point, we're going to pass in the usual to our estimator spec, which we're going to return. And so we have the mode, loss function, and then also our eval metric ops. Now we can move on to the main function, because that's the end of our actual model function. So here we have just a default mode equal train, and then our model parameters would be learning rate. In this case, we can call the argument whatever we want. It doesn't have to be params. It only needed to be params for our actual model underscore fn. So whatever we pass into the estimator. And so this is what I was saying that actually shouldn't have been hard-coded in, but it's okay because we're using the same value anyway. But just know if you want to, this is where you can pass params with the keyword of learning rate. Okay, so now we need to load the training data. This is where I mentioned that we would call a function for our data to actually pull our data in to act on with our classifier. In this case, this is where we're loading in our MNIST data using the TensorFlow API because they already have some data sets, and specifically the MNIST data set. And here we have train data, which we're going to use mnist.train.images. So that'll give us a NumPy array of flattened images. And of course we want our train labels. So here we use np as array in order to actually get a proper array for ourselves from the training labels. And we want to set the D type to int32. Then we have our evaluation data, and we're just going to use eval data for our predictions as well. So mnist.testimages, again, our NumPy array, and eval labels, we treat that the same. We need to do np.asArray and get test labels as opposed to train labels. Again, same data type. This is where we create an estimator. That's going to be before anything having to do with mode. We always have this particular estimator because all we have to do is define this object with our model function and params equal model params. So that's what we passed as an argument up here. And then this model dir, that's just a directory basically to save our logs to, as well as our global step. Everything that really we need in order to pick back up where we left off. Bear in mind that's not the same as saving our model. And here's where we're actually going to train the model. So if mode equal train, and this is just our own definition of train. We can use anything we want. It could be T for that mode, P for predict, E for eval, whatever we like. It doesn't actually have to be the specific TensorFlow values that we defined up here. These only need to be in the model function. And so if the mode is train, then we're going to create that train input. This is where we, earlier, when describing the model structure, we had an asterisk right here. So this is the train input function. And this is where we're going to use our tf.estimator and that NumPy input function that we mentioned earlier. And that's specifically because we have NumPy data. So we're going to say that x equals this dictionary with x being the train data. And then y is equal to train labels. And here's where we are going to set our batch size. So we'll set that to 100. The number of epochs that we want to train on, 10 overall is going to be pretty necessary. It should be sufficient. We're going to set shuffle to true so that it's going to just randomly shuffle the images. And here's where we use the classifier, which is the estimator that we created up here. So that's our MNIST classifier, and we're just going to call the method train on this, passing our train input function that we just defined as its input function. Now, if it's not train for the mode, but it's predict, then we're going to do this. We're going to create our input function for predict specifically, which again uses the NumPy input function. So same thing, but we don't need a batch size, and really we're just going to set number of epochs to 1. We don't need multiple epochs for predictions. And we're going to set shuffle to false because that doesn't matter. And here's where we're going to actually get our predictions. So instead of just calling the method on our classifier, because this particular one is going to return our predictions, we need to set preds equal to our MNIST classifier dot predict. And for our input function, we're passing this. And then when we're done, because our mode is predict and it's actually returning a value, we actually need to return our NumPy array. So here we're going to create a NumPy array of all of our predictions. We specifically need this because it returns an iterator rather than an actual array of objects. So we're just going to use this list comprehension format, say p for p in preds, and we'll see what that output looks like in just a second. But that's going to give us basically just one dictionary for every single prediction. Now, if it's not predict, but if the mode is eval, then we're going to actually evaluate our model. So same thing, we're going to create these input functions, set the data, but because we're evaluating, again, we need to pass in the labels. Number of epochs to 1 once more because we don't need multiple epochs for evaluation, and shuffle to false. Now we have the evaluation results, which we get from this particular method of evaluate, but we're going to just print these results instead of actually returning something. While we could run this in here, on this particular computer where I'm doing this recording, it would be CPU only, so it would be slow. I ran this on a GPU on another computer, and for each 100 steps, it takes less than a second. But if I were to run it on a CPU, it'd take about 30 seconds for each 100 steps, so it would go much slower. So this is what the output looks like if we run the main function as the default, which we set to train before. So this is what our output looks like. You can see that it shows that it's extracting that data, and then it's showing essentially every 100 steps. So we have here step equal 5501 and 5601, etc. So it's showing us our loss, and for most of these it's also showing how long it took. So once we're down to the end, really I could compress this actually. All right, so at the end of all of this, we end up with our final step. So this is the loss for our final step, which is 0.2. And then if we run the main function with mode equal eval, then that'll evaluate, and we can see that there's an accuracy of about 95%, which is great, and a pretty low loss of 0.16. We can also see that we have our global step. And then finally, let's go ahead and get our predictions. So we're going to call main with mode equal predict, and we make sure that we set preds right here so that we can collect those results. And it's going to get to the end, and then once we actually call just the first value from preds, then we're going to see this dictionary. So this gives us classes and probabilities. So just the same as that dictionary that we created before, that preds dictionary. So this right here has the probabilities for each of the 10 classes. So you can see that, for example, this would represent the digit 0, and so that has a very small probability. Earlier, I just realized I said that we're using digits 1 through 10. That's not the case. It's 0 through 9. And so, very small probability for this, and we can look for this one right here. We have about a 99% probability of having class, or having the digit 7. So, most likely, given how high that probability is, that's probably a correct classification. All right, so that is everything for the convolutional neural network.